Hi guys, here's a video going over section 2.2, polynomial functions of a higher degree. After watching this video, you should be able to find the zeros of a polynomial, write polynomial equations, as well as graph polynomial functions. So the first thing we need to do is establish what a polynomial is. So there's your definition of a polynomial. So let f of x be the polynomial f of x equals a(n) times x to the nth power plus dot 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 plus a1 times x plus a0. Do not get bogged down by the structure of this definition. You're going to see it in terms of actual numerical values. But you do need to know these three things: degree, leading coefficient, and number of turning points. So your degree is n, which is also the highest exponent. So in this case, highest exponent. Leading coefficient is the number in front of the variable with the highest exponent. And the maximum number of turning points is going to be your n minus 1 or your degree minus 1. Maximum number of turning points will tell you how many times your graph turns. So in this case, I have a turning point right here and a turning point right there. Okay. So the first thing we're going to look at is something called a leading coefficient test. So a leading coefficient test looks at the degree of your polynomial as well as the coefficient, and it will allow us to look at what's happening at the ends of your graphs. So for example, if the degree is odd and the leading coefficient is positive, what your graph is going to look like is something like this. My polynomial is going to go up to the right and down to the left, and everything in between can really be anything depending on the actual polynomial. If my leading coefficient is negative, it's going to be the opposite, where my graph is going to go down to the right and up to the left, and again, the middle can kind of do whatever it wants based on the actual polynomial. I'm going to go ahead and shorten this arrow. Okay, so with each of those graphs, I'm going to write out the end behavior. So the end behavior is a statement that's going to talk about what's happening on the left-hand and the right-hand sides of my graphs. So end behavior, you always start by writing this as x approaches infinity, f of x approaches, and then we're going to figure out what goes right here in a little bit. And then again, as x approaches negative infinity, f of x approaches, and I'm going to use the graph to fill in those blanks. Now that statement is going to be the same for my second graph, so I'm going to go ahead and write it over here. So anytime you're talking about end behavior, your statements are going to look exactly the same regardless of the graph or the polynomial. What is going to be different is what you're going to put on these lines, and those lines are based off of what's happening on the graph. So if I look at my graph for my leading coefficient being positive, I have as x approaches positive infinity. So this first statement is what is happening as your graph moves to the right. So as x approaches positive infinity, what's happening to my graph? Well, my graph is going up, as you can see. So that is going up towards positive infinity. As x goes to negative infinity, that is what is happening on the left-hand side of your graph. My graph is going down towards negative infinity. I'm going to do the same thing for this one. So as x moves to the right towards positive infinity, my graph is going down. And as x moves to the left towards negative infinity, my graph is going up. So a couple things to pay attention to. For this one, my leading coefficient was positive and negative with a degree that was odd. So if you'll notice, when you have an odd degree, your ends, these are my ends, your ends are going in opposite directions. Okay, so that's something that you need to remember. Odd degrees are going to go in opposite directions. Now we're going to do the same thing as if my degree were even. So we're going to see what that looks like. I'm going to draw my two graphs. So if my leading coefficient is positive, I'm going to go up to the right. I'm also going to go up to the left, and then in between could really be anything based on the actual polynomial. If my leading coefficient is negative, I'm going to go down to the right as well as down to the left, and again, the middle can be anything based on the polynomial. So if you'll notice, your even degrees are going to have ends that go in the same direction. I'm going to fill in my end behavior so I can make a note as to what is happening on the ends. And this information is quite valuable when you are sketching graphs, which we're going to do in a little bit. So as x approaches infinity, f of x approaches. As x approaches negative infinity, f of x approaches. Now for this one, if I look at when my leading coefficient was positive, on my right-hand side, it was going up towards positive infinity, left-hand side also towards positive infinity, because my ends are going in the same direction. When my leading coefficient is negative, going to the right, my graph is going down, and to the left, my graph is also going down, because again, it was an even degree, so your ends are going in the same direction. Okay, so now let's actually apply the leading coefficient test to some polynomials. So it says describe the right and left-hand behavior of the graph of the polynomial function. So left and right-hand behavior is the same thing as describing end behavior. And in order to do that, I need to know two things. I need to know my degree, and I need to know my leading coefficient. So degree is your highest exponent. Sometimes your polynomial is not written in order, so make sure you look closely for your highest exponent. Degree is 6, which I'm also going to make a note is even. And my leading coefficient is the number in front of the variable with the highest exponent. So in this case, it's -1, and I'm going to make a note that it is negative. Now, these two values, the 6 and the -1, I actually don't really care about the numerical values of them. What I do care about is whether they are even and negative, even or odd, and negative and positive. Okay, so now I'm going to write out my statement for end behavior. Again, your statement is always the same, regardless of the problem. Okay, so without actually looking at the graph, we need to figure out the end behavior. Now, if your leading coefficient is negative, what that's going to do is that's going to create a negative infinity for your first infinity. So your leading coefficient is always going to tell you whether your first infinity is positive or negative. And your degree, whether it's even or odd, is going to tell you whether these two infinities are going in the same direction or opposite directions. Well, since my degree is even, that means they should be going in the same direction. So the second infinity is also negative infinity. And this right here is your left and right hand behavior. All right, next one, I'm going to find my degree. Degree is highest exponent, which is 5, which I can see is odd. Leading coefficient is the number in front of the variable with the highest exponent, which was 2.1, which I can easily see is positive. So I'm going to write my statements as x approaches infinity, f of x approaches, as x approaches negative infinity, f of x approaches, and again, your leading coefficient is going to tell you the sign of your first infinity. So since my leading coefficient was positive, that means my graph is going up to the right towards positive infinity. And because my degree is odd, that means my ends are going in opposite directions. So this one is going to go towards negative infinity. And there is your end behavior. The next thing we're going to talk about is zeros and multiplicity of repeated zeros. So if f is a polynomial and a is a real number, then x equals a is a 0, which means these two things will also be true. So x minus a is a factor, and then a0 is going to be an x-intercept. Sometimes your factors are repeated, meaning that your factor is going to have some sort of exponent. So a factor x minus a to the k is a repeated 0 of multiplicity k. And then these two pieces of information are super helpful when we're creating a graph. So when k is odd, it's going to cross at that particular 0, and when k is even, the graph is going to bounce at that particular 0. And I'll come back to this once we do the example dealing specifically with graphing. So for the second example, we just want to find the zeros. So it says find all the real zeros of the polynomial, determine the multiplicity of each zero, and determine the maximum number of turning points. So anytime I'm trying to find the zero of a polynomial, what I'm going to do is I'm going to set my polynomial equal to 0. And what you're left with is hopefully a polynomial that is factorable. So I want to see what these two terms have in common. They have a 2 and an x squared in common. Now, if your leading coefficient is ever negative, you need to factor out the negative with the GCF. Otherwise, it's going to become more difficult to factor later on. So from here, when I take out a negative 2x squared from negative 2x to the fourth, that leaves me with x squared. When I take out a negative 2x squared from positive 2x squared, that leaves me with negative 1. And then x squared minus 1 is one of your special cases for factoring. It's a difference of squares, so that factors to x plus 1 and x minus 1. Once your polynomial is fully factored, you are going to then find the zeros. So in order to do that, you are going to take each one of your factors and set it equal to 0. So I have negative 2x squared equals 0, x plus 1 equals 0, x minus 1 equals 0. For the first one, I'm going to divide by negative 2. I get x squared equals 0, square root of 0 is just 0. For my second one, I'm going to subtract 1 from both sides, so I get x equals negative 1. And then for my third one, I'm going to add 1 to both sides, so I get x equals positive 1. Once you have your zeros listed, you can go ahead and find the multiplicity. So your multiplicity comes from the factor that the 0 came from. So I'm going to go ahead and start by listing out my zeros. So I had a 0 at 0, and then I'm going to state the multiplicity. I had 1 at negative 1. I'm going to state the multiplicity, and then I had 1 at positive 1, and I'm going to state the multiplicity. So for 0, I'm going to go back and look at the factor that it came from. So the factor that the 0 came from was from negative 2x squared, and I'm going to look at the exponent on that factor. That exponent is actually going to tell you what the multiplicity is. So since my exponent was a 2, that means my multiplicity is going to be 2. For negative 1, that came from this factor, and that factor does not have an exponent, so anything that does not have an exponent has a 1 there. So both negative 1 and positive 1 have multiplicities of 1. Now, if you are currently confused on multiplicities, you'll see it used once we actually get to the graph. So right now we're just stating the multiplicity, but it'll make a lot more sense once we're actually creating the graph. And the last thing we want to do is find the maximum number of turning points. Max number of turning points. And that is your degree minus 1. So my degree is 4 minus 1. So my maximum number of turning points is 3. So that means if I were to actually graph this, your graph would have 3 turning points. So it'll have 3 max or mins. Okay, so now let's actually go through the process of graphing the polynomials. So to graph the polynomials, you're going to go through this 3-step process, apply the LCT leading coefficient test, find the real zeros, and then actually create the graph. So I'm going to start by applying the leading coefficient test. So I need to find my degree and my leading coefficient. Degree is your highest exponent, which is 3, which I'm going to make a note is odd. Leading coefficient is 2, which I'm going to make a note is positive. So now I'm going to list my end behavior. So as x approaches infinity, f of x approaches. As x approaches negative infinity, f of x approaches. So the graphing problems actually encompass all of the previous examples into a single problem. So my leading coefficient is positive, so that means my first infinity is positive. My degree is odd, which means my infinities are going in opposite directions. So positive infinity to the right and heading towards negative infinity on the left. So that is part A. For part B, I want to find the real zeros. So I'm going to take my polynomial and I'm going to set it equal to 0. So I have 2x cubed minus 8x. I want to take out the GCF, so they have a 2 and an x in common. That leaves me with x squared minus 4. X squared minus 4 is a difference of squares, so that's x plus 2, x minus 2. And then I'm going to take each one of these factors and set it equal to 0. So I have 2x equals 0, x plus 2 equals 0, x minus 2 equals 0. First one, divide by 2, x equals 0. Second one, subtract 2, x equals negative 2. Third one, add 2, and x equals positive 2. Now underneath all of these, I'm going to go ahead and list the multiplicity as well. And again, for the multiplicity, I'm going to go back and look at the factor that it came from. So 0 came from this factor, and this factor did not have an exponent, so it's like having a 1 there. Negative 2 came from this factor, and again, that exponent is just a 1. And positive 2 came from this factor, and that exponent was also a 1. It's like having x to the 1, x plus 2 to the first, and x minus 2 to the first. And now that we have all of that information, we can go ahead and sketch the graph. So my zeros are at positive 2 and negative 2, so I'm going to go ahead and go to 3 on my x-axis. Same on my y. Now these graphs are just sketches. They're not going to be 100% accurate. And then the next thing I'm going to do is I'm going to plot my zeros. So I have a 0 at 0. Your zeros are also x-intercepts, so they're on your x-axis. 1 at positive 2 and 1 at negative 2. Now to figure out what my graph is actually doing, I'm going to go back to this piece of information. That tells me what's happening on my right side and what's happening on my left side. So on my right side, my graph needs to be going up towards positive infinity. On my left side, my graph needs to be going down towards negative infinity. So I'm going to the rightmost 0 and the leftmost 0. And then now I'm going to look at my multiplicity. So at negative 2, my multiplicity is 1, which means I'm going to cross at that 0. At 0, multiplicity is also 1, which is odd, so I'm going to cross at that 0. And then at positive 2, multiplicity is odd, so I'm going to cross again. And then I need to logically connect these pieces together. Now, if you were to graph this in the calculator, these peaks, these two, might be way up further than what I have written down, but again, these are just sketches. Okay, so what I'm looking for is I want to see that your zeros are in the right spot, that your ends are going in the right direction, and that you connected them in a way that makes sense. All right, let's do another one. So with this one, I have negative x to the 4th plus 25x squared. Again, I'm going to go ahead and do the leading coefficient test. So to do that, I need to know my degree, which in this case is 4, which I'm going to make a note is even. My leading coefficient is negative 1, and I'm going to make a note that that is negative, obviously. And then from here, I'm going to write out my end behavior. So as x approaches infinity, f of x approaches. As x approaches negative infinity, f of x approaches. And then, just like with the last one, your leading coefficient will tell you the sign of the first infinity. And since this degree is even, that means my infinities are going in the same direction. So this one will also be negative infinity. Now we need to find the zeros. So to find the zeros, I'm going to take my polynomial and set it equal to 0. I'm going to factor it. Now, if you do have a negative as your leading coefficient, you need to factor it out with the GCF. So in this case, my GCF is x squared, so I'm going to take out a negative x squared. That's going to leave me with positive x squared minus 25. I'm going to continue to factor. This is a difference of squares, so x plus 5, x minus 5, and then I'm going to take each factor, set it equal to 0. So negative x squared equals 0, divide by negative 1. I get x squared equals 0, square root, so x equals 0. For my next one, I have x plus 5 equals 0, so that gives me x equals negative 5. And then x minus 5 equals 0, so x equals positive 5. And then for my multiplicity, I'm going to look to see where my 0 came from. That one came from negative x squared, so my exponent on that factor is a 2, so that's going to have a multiplicity of 2. X minus 5 came from this factor, which has an exponent of 1, so a multiplicity of 1. And x equals 5 came from this one, also with a multiplicity of 1. And now that we have all of that information, we can go ahead and sketch the graph. So I have negative 5 and positive 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The y-axis doesn't really matter all that much just because we're just making general sketches. I'm going to go ahead and plot my zeros. So I have a 0 at 0, positive 5, and negative 5. And then from here, I'm going to look back at my end behavior. Both ends are going down towards negative infinity. So on my right side, down towards negative infinity, as well as on my left side. Now to fill in the rest of the graph, I'm going to look at my multiplicity. So at negative 5, my multiplicity is 1, which is odd, so that means it's going to cross at that 0. Same thing at positive 5, odd multiplicity is going to cross. And then at 0, that one has a multiplicity of 2, which means on your graph, it is going to bounce. So I need to somehow connect these two ends together in such a way that it makes sense that it connects with the other 0. So in order to do that, I'm going to go ahead and go up. I'm going to hit this 0, and since it needs to bounce, I'm going to come back up, and then I'm going to connect it to the other side. And there you have it. So this last example, what you're doing is I'm giving you the 0, so it's kind of working backwards from our last example. I'm giving you the zeros and the degree, and then from there we need to write out the polynomial. So this n equals 2, that represents the degree. If you recall, degree is your highest exponent. So my degree is 2. I have a 0 at x equals negative 1, so when I want to set up the factor, it's always x minus what my 0 is. So x minus negative 1 becomes x plus 1. Now my degree is supposed to be a 2, which means I should have an x squared. But if I look at what I have right now, all I have is just an x plus 1. So that means this 0 is a repeated 0, which also means this factor is a repeated factor. And then from here, I can go ahead and multiply it out, just using good old distribution. That leaves me with x squared plus 1x plus 1x plus 1. Combine like terms, and I have f of x equals x squared plus 2x plus 1. And if you'll notice with your final answer, I have that x squared for that degree of 2. All right, for letter B, I'm going to go ahead and set up my factors. My degree for this one is 3, which means in the end, I should end up with an x cubed. But let me set up my factors. 0 at negative 3 gives me the factor of x plus 3. 0 at 0, x minus 0. 0 at 7, x minus 7. The x minus 0 looks weird, not a fan, so I'm just going to write that as just x. And that x in the middle also looks weird, so I'm going to go ahead and distribute it. Now when you distribute the x, you can only distribute it into one parenthesis, one factor. Do not put it into both, because then your degree is going to be a lot higher than 3, as it should be. So I'm just going to distribute it into the second parenthesis. So I still have my x plus 3 right here. When I distribute the x, that's x squared minus 7x. And then I'm going to go ahead and multiply these two together. So I have x cubed minus 7x squared plus 3x squared minus 21x, combine like terms, and I get f of x equals x cubed minus 4x squared minus 21x. All right, so this was quite a long section, covered a lot of stuff, leading coefficient tests, creating graphs, finding zeros, as well as finding the polynomial equation when you are given the zeros. So feel free to watch this video again if you are confused, or just go back to the specific parts that you need to see again. All right, adios.